Welcome back, everyone, to another journey through probability and statistics. Last time, we worked out what a random variable really is. You are watching 99.73%, the number that explains the world. The rest is the unexpected. Today, we zoom in on the most common family of them all. Let's get started. How many heads in a handful of coin flips? How many defective parts came off the line this morning? A great many real-world questions have answers you can count. 1, 2, 3, and so on. This is the world of the discrete random variable. Be careful, though. Discrete does not mean whole numbers, and it does not even mean finite. By the end of today, that definition will be sharp, and you will be able to describe any discrete variable completely using two tools. Before we go anywhere new, 30 seconds on where we left off. A random variable is not really random and not really a variable. It is a rule, a translation machine. It takes a messy, real-world outcome and turns it into a clean number. On the right, the values. In between, our machine, x. Flip two coins. Two coins give four outcomes. Heads, 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 tails, tails, heads, tails, tails. Let x count the heads. Watch each outcome feed in, one at a time. 2, 1, 1, and 0. One number each. One arrow out of every outcome. Never two, never none. In symbols, x from omega to the reals. Heads, heads to 2, each mixed outcome to 1, tails, tails to 0. Keep that picture. Now, a new question. What kinds of numbers can come out of that machine? The set of possible values has a name, the support, and its shape is what today is really about. For the coins, short and finite, 0, 1, 2. 3 isolated values, nothing in between. That is the support of x. Here is the first myth to bust. Students often assume these values have to be whole numbers. They do not. Picture a stack of exam papers, each one carrying a grade. Grades run from 0 up to 4 in steps of 1/10, 0.1, 0.2, and so on. 41 possible values, and hardly any of them is a whole number. Not whole, then, only separated. That is what matters. Myth number 2, that a discrete variable can only take finitely many values. Flip a coin over and over until the very first heads shows up. It might take one flip, heads, straight away, or 2, tails, then heads, or 3, or 4. In principle, it never has to stop. 1, 2, 3, and onward, forever. Infinitely many values, and still we can list them one by one. We call that countable. Myth 3, that the values must be evenly spaced. Think of a lottery ticket. It might pay nothing at all, or 5, or 20, 100, 500, 1,000. The gaps are wildly uneven, and it makes no difference at all, still discrete. That is 3 myths, all of them busted. If it is not about being whole, not about being finite, and not about being evenly spaced, then what actually makes a variable discrete? Back to the 2 coins and the numbers they map to. Each value takes its own share of the probability, a quarter, a half, a quarter. One idea ties it all together. Each value stands alone, like a stepping stone, with open space between them, each one on its own. That is the picture. Values that line up with a gap between each pair. X maps omega onto an at most countable support. And that is what discrete really means. To see the contrast, let us visit the opposite world, the continuous one. Picture a rolling mill pressing a sheet of metal with a sensor reading its thickness. Freeze the line and read the gauge. It reads 4.9 millimeters. Now zoom in. Between 4.9 and 5.0, the reading could be 4.93. Zoom again. 4.928. Finer still. 4.9284. No matter how far we magnify, there is always another value squeezed in between. No gaps, no isolated stepping stones. The values are packed infinitely tight. The support is no longer a list. It is a whole interval of the real line. That is a continuous variable. And a story for another day. Today, we stay in the world of gaps, where we can point at each value and ask, how likely are you? We start from something you already know, the probability that the variable, capital X, takes some specific value, little x. That quantity gets its own name and symbol, P sub x of x, the probability mass function, or PMF. With only one variable in play, we usually drop the subscript and write P of x. Back to the two coins. Every outcome maps to a number, and those numbers land on an axis. Why the word mass? At each possible value, we drop a small weight. 1/4 on 0, 1/2 on 1, 1/4 on 2. The heavier the weight, the more likely that value. Probability is not smeared along the line. It sits concentrated like mass on each isolated point. Any honest mass function must obey two simple rules. First, no weight can be negative. Probabilities never fall below 0. Second, gather up every weight on the line, drop them all on a scale, and the total must be exactly 1. The sum of P of x over all values x equals 1. Stand those weights up as bars and you get the picture we will use all day. The height of each bar is its probability, and everywhere in between, 0. Non-negative and summing to 1. Any function obeying those two rules is a valid PMF. Let's put them to work on something familiar. 3 coin flips. Let x count the heads. Support 0, 1, 2, 3. Flip them once and you get one concrete outcome. Heads, tails, heads. 2 heads, so x equals 2. There are 8 equally likely outcomes in all, and each value of x collects the ones that match it. One outcome gives 0 heads, 1/8. 3 give a single head, 3/8. 3 give 2, 1 gives all 3. 1, 3, 3, 1 are counts of outcomes. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Counting outcomes is precisely what a combination does, so the whole table collapses into one formula, 3 choose x over 8 for x from 0 to 3. Rewrite the 8 as 1/2 cubed, and you get 3 choose x times 1/2 to the x times 1/2 to the 3 minus x. That shape has a name, the binomial. One formula, one table. The same information written 2 ways. Now, a second flavor of PMF. Same recipe, new setting. Roll 2 dice. X is their sum. First die plus the second. How likely is each total? Lay out a 6x6 grid, one die along the rows, the other along the columns. First cell, a 1 and a 1. Their sum is 2, and that is the only way to make it. 3 happens 2 ways, 1 and 2, or 2 and 1. Fill the rest. Every diagonal shares one sum, 2 up to 12. Now lay those totals along an axis, one column per sum. Slide each diagonal straight down onto its column, and the counts become a mass diagram. 7 sits on top with 6 ways out of 36, and it falls away symmetrically either side. Where does that come from? The denominator is the 36 equally likely cells. The numerator is the diagonal length, which drops by 1 for every step away from 7. Hence, 6 minus the absolute value of x minus 7 over 36. And the same story once more as a table. 2 examples, 1 lesson. Find the outcomes, count them, and you have your PMF. Now for the real thing. A crate of 12 parts, fresh off the line, each one either good or defective. and let x be the number of defective parts. Each one goes bad with probability 0.3. Start with the easiest case. Every single part is good. The chance of that is 0.7, 12 times over, and there is only one way for it to occur. Now, 1 defective, 11 good, 1 bad, but it can sit in any of the 12 slots, so there are 12 such selections, all equally likely. 2 defective. Now choose which 2 slots go bad, 66 pairs. 1, 12, 66. These count the ways of selecting which slots go bad, and selecting is exactly what a combination does. 12 choose 0, 12 choose 1, 12 choose 2. So one formula covers every case. P of x equals 12 choose x times 0.7 to the 12 minus x times 0.3 to the x for x anywhere from 0 to 12. And there it is again, the same binomial we met with the 3 coins. An entire film on it soon. Plug in every x and the whole mass function falls out. 13 values. Chart it and you see the shape instantly. It climbs, peaks, then tails off, lopsided to the low end. 3 defective is the most likely count on this line. But that only answers exact counts. For everything else, we need one more idea. So far, we have only asked one thing. What is the chance of a single value? In practice, we more often want, at most, how many, and that question has a name of its own. The cumulative distribution function, f of x, the probability that x is less than or equal to x. Back to the production line, shrunk down to just 3 parts. Same binomial shape as before, support 0 to 3. 4 possible counts of defective parts. Feed the 4 support values into that formula, and the masses fall straight out. Plot them and get ready to accumulate left to right, each probability a weight dropping onto its point. Now, a little cart sweeps that line, scooping up every weight it passes. Before the first value, the cart is empty-handed, so f of minus 1 is 0. The moment it reaches 0, it grabs that weight, and f jumps straight up to 0.343. Push on to 0.5. Nothing new to collect, so f does not move. Still nothing at 0.9. Flat. Cross 1, and it jumps again. The cart now carries the first 2 masses together. Cross 2, now the first 3. Cross 3, 1. The cart now holds every weight there is. F is still 1 at 4 and stays there forever after. Flat, then jump. Flat, then jump. In a discrete world, the CDF is always a staircase climbing to 1. And once it is built, it still has more to tell us. The PMF and the CDF are not 2 separate ideas. They are 2 views of the same thing. Adding up the PMF builds the CDF. We can also travel backwards. Look at the staircase again, and this time at the risers. Each riser is precisely the mass sitting at that point. Measure the first 3 and you read them straight off the table. And zoom right in, even the last tiny step carries a real mass. In symbols, P of x equals f of x minus f of x just before the jump. The size of that step hands it straight back. So from the staircase alone, you can rebuild the whole PMF. And the staircase itself is easy to write down. Between one jump and the next, nothing is collected, so f holds still. On each stretch, it is a constant, the height reached at the last jump. Below 0, it has collected nothing. From 3 onward, it has collected everything. 5 stretches, 5 constants. Now for the trap that catches almost every student. Less than and at most are 2 different questions. X at most 1 is f of 1, 0.784. That includes the jump at 1. But strictly less 1 stops just before it and misses that jump entirely. 0.343. The gap between them is that 1 point's mass, nothing more. In a continuous world, one exact value has no probability at all. Here, it carries real weight, and that is why the staircase jumps. One clean rule to carry with you. X greater than A, but at most B, is f of B minus f of A. So the chance of 1 or 2 defectives is f of 2 minus f of 0, which comes out at 0.63. So handle your inequalities with care. Each one can quietly change the answer. That staircase is not arbitrary. It always obeys 4 rules. Let's name them. 1. It stays between 0 and 1. It is a probability after all. 2. It never goes down. Moving right, we only ever collect more weight. If x1 is at most x2, then f of x1 is at most f of x2. We call that non-decreasing. 3. Far to the left, it flattens to 0. Far to the right, it settles at 1. 4. And this is the subtle one. At each jump, the function takes the value at the top of the step, not the bottom. We say f is right continuous. Bounded, non-decreasing, with those two limits, and right continuous. Every discrete CDF you meet will look like this staircase. Let's pull it all together. Everything today rests on one picture and two tools. A discrete random variable is a rule whose values are isolated, separated points you can count, like stepping stones. First tool, the probability mass function, how much weight sits on each point. Second, the cumulative function, everything gathered so far. Add up to go one way, read the jumps to come back. Two views, one variable, the same information. Certain stories keep recurring, counting successes, waiting for a first success, tallying rare events. They have famous names. Each is a PMF with its own shape, and each deserves its own film. There is one more question hiding inside every chart we have drawn today. If you had to summarize a whole distribution with a single number, where is its center? Picture those masses sitting on a beam, the point where it balances. And how far do they scatter around it? That balancing point and that scatter are called expectation and variance. That is where we are headed next time. Thank you so much for watching. You now hold the two tools that unlock every discrete random variable there is. Practice reading a PMF and climbing a CDF. I will see you in the next one, where we learn to find the balance point of randomness itself.